There's one thing I want to talk about before we talk about finding the seasons, and that's just a little bit on angular measures. And we talked a little bit about this for going outside and using your fist as a measure of angles, but I just want to make sure we all understand what angles we're talking about, because these angles are how we measure things on the sky, because we don't really know how far away things are necessarily, so we just use angles. And to give you an idea, just to remind you, 1 degree has 60 arc minutes in it, and it has 3,600 arc seconds. So it kind of works like a clock, except instead of a minute or second of time, we have a minute or second of arc, and that's equal to 1 degree. And in astronomy, one of the fundamental units is an arc second, because things tend to be pretty small. So if you want to get an idea of what an arc second is on the sky, if you take a really well-sharpened pencil at arm's length, hold it all the way out, the tip of the pencil is about 1 arc second on the night sky. And so that gives you an idea of how precisely we can measure these things. And in fact, oftentimes we measure things to milli-arc seconds, which is a millionth, or sorry, a thousandth of an arc second is a milli-arc second. So we do some pretty precise measurements with these angles. If you're outside in the night and you want to do angular measures for yourself, again, all these things are with your hand held at arm's length. So your finger, the width of your finger is about 1 degree. And you can check this because the moon is about 1/2 degree on the sky. So if you hold out your finger and cover the moon with your finger, you should cover about half, or you should cover all of it by a little bit extra. And it should be about a degree, give or take, within a factor of 2. Your fist is about 10 degrees, and you can use these to measure altitude and azimuth. So if you ever want to say you found something in the night sky and you don't know what it is, send me the altitude and azimuth coordinates on what time you observed it, and I can go check that for you. Okay, so now that we've got an idea of where things are and how things move in the night sky, we need to talk a little bit about the motions of the planets, because that's the motion of the Earth in particular is what gives us the seasons that we experience. So first of all, let's talk about the motion of the sun and the Earth. And the question I have for you, which I've already given you the answer here, is does the Earth revolve on its axis once each day? And this is a subtle question because the answer is actually it depends on what you mean by a day. We have 2 different types of days. We have the amount of time it takes the Earth to rotate on its axis. That's called a sidereal day or a stellar day, because we're saying how long does it take the Earth to rotate on its axis with respect to the background stars. But we also have a solar day, which is how long it takes the Earth to rotate with respect to the sun. And the reason those 2 things are different is because the Earth moves in its orbit. And so while it takes a certain amount of time to rotate just intrinsically relative to the stars, we've moved with respect to the sun, and so it takes a little bit longer for the sun to catch up in the sky with where it was the day before. So the thing we call the sidereal day is a little bit shorter than what we call the solar day. So this solar day is something we're all familiar with. It's noon to noon. Right? So if I wake up at noon, or if I go outside at noon and want to wait for a full day, I wait until noon the next day. And that's what we call 24 hours. That's a definition of a day. However, that is not the rotation period of the Earth. The rotation period of the Earth is actually 4 minutes less than that. And so if you really want to amaze your friends, if they ask you how long a day is, just say which one, and they'll be really impressed with you that you'll know the difference. But the reason that the solar day is a little bit longer, if you look at this picture here, is that if we imagine an observer who's outside at noon with respect to the sun and the stars on one day, if we wait for one rotation, the moon or the sun has moved, the Earth has moved with respect to the sun. You get up here relative to the background stars before you rotate over to where you would be relative to the sun, and that's about a 1 degree difference per day, and that's what gives that 4-minute difference in the lengths of the days. And so this length of the day, the actual rotation period of the Earth is called sidereal, and that's Greek for with respect to the stars. And so that means that we have the actual rotation of the Earth, which is the physical rotation, and then we have what we call the solar day. And there are even other kinds. There are lunar days. There are, I mean, you can define the day relative to anything you want. You could define the day relative to the position of Mars if you really wanted to. But those are the two that we talk about all the time, the sidereal day, which is 23 hours and 56 minutes, and the solar day. And astronomers, you're going to love this. We can actually buy watches that keep sidereal time, you know, if we don't want to deal with the solar day and we want to stay on sidereal time. Okay. So the sun, the Earth is moving with respect to the sun. We orbit around the center of the sun, the center of the solar system, which has the sun in it, and it's this motion of the Earth that causes the variations in the season because the planet happens to be tilted. So if we look at the reasons why we get different types of weather in the seasons, there's really two big ones. There is the direct versus indirect sunlight, and that happens when, because the Earth is either tilted away or tilted towards the sun, you get direct or indirect light. And you know, you've experienced this. If you go outside in the summertime, the sun feels hotter than it does in the wintertime. It's the same sun, but it's just the fact that in one position it's lower in the sky versus higher in the sky that makes it feel warmer. The other thing that happens, which I'll show you in just a moment, is that the length of the day changes as we go through the year. There's a very subtle third effect which has no consequence for the Earth but becomes really important for other planets around other star systems, and that is the ellipticity of the orbit. You can get some really elliptical orbits where the planet is significantly closer to the sun when at its closest point than its farthest away point. That is not the case for the Earth. The Earth's orbit is effectively circular, and in fact we are closer to the Earth, or closer to the sun, in winter in the northern hemisphere than we are in summer. So it has a very minimal effect, this ellipticity. The two main ones are going to be the direct and indirect sunlight and the length of the day. And the fun thing is that both of these are caused by the exact same thing, which is the tilt of the Earth. And that's the thing I want to show you. I've got a little diagram here that sort of demonstrates this, but we can play around this with stellarium a little bit easier. This is showing you standing someplace on Earth and seeing what happens at different times of year. If we think about the winter solstice, which is December 21st, the spring equinox or the fall equinox, or the summer solstice. And that's the highest position of the sun changes relative to the season. So in the summertime, the highest position of the sun is much higher in the sky than in the wintertime. But the sun makes the same arc around the Earth, or I should say the Earth's rotation is the same regardless of the seasons, and so we just get this shorter path length depending on the season. So in the summertime, the sun actually rises north of east and it sets north of west, which makes a much bigger arc in the sky than at either the equinox or the winter solstice. So let's take a moment to see that in our stellarium program. Okay, so here we are, at Ogden, Utah, and let's go ahead and pick a date. Let's do the 21st of December. And we'll leave the time where it is. Okay, so I changed this to the 21st of December, so that's the month. I believe that's the month. Let's just double check here. Could be European. Yep, it's the month. Okay, so 12th, 21st, this is the solstice, right? So this is the shortest day of the year. And I want to look south because it's a little bit easier to see what's going to happen if I look south. And you can see, I'm just going to run this, and we are at, let's see, what time are we at? Let's make this in the morning. Yeah. Okay, so here we are at sunrise, and already you can see what's going on here, that at sunrise we are very much south of east by a significant amount. In fact, you can check the azimuth of the sun. If I click on the sun, you can check the azimuth of the sun, if we can see it, and it is, the azimuth is 122 degrees. This is 90 degrees, right? East is 90 degrees, so it's almost 30 degrees south of east at the summer solstice, or at the winter solstice. Now if I hit play, we can watch the sunrise and just watch the arc through the sky and look at how low the sun is in the sky during the wintertime. Here we are, its highest point is going to be due south. Boop. There we go. And then, if we wait a little bit, it's going to set, and it will not set in the west. It will set about 30 degrees south of west. Boop. Okay, nice, huh? All right, so now let's send that back. Well, let's do this. Let's go to a different time. Let's go to the summer solstice. So if I go summer, that's going to be June 21st, roughly. Boop, 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 boop. Okay. And then I'm going to do this a little bit earlier in the morning because the sun rises earlier in the morning. And here we are looking east on the summer solstice. And you can see, again, 30 degrees north of east. The sun is so far further north. And if I hit play, whoop, oh geez, yikes, look out. Are we still on the summer solstice? Yikes. Yes, okay. Let's go back, huh, shall we? We really go crazy with this program. Okay, there we go, boom, okay. Only click it 3 times, there we go. And, see, we can't even see the sun, it's so high in the sky. Whoa, there it is. It's so high in the sky we can't even see it in this field of view. But if I go look at west again and let this thing go forward, you will see that the sun should set north of west. Where is it? There we go. Ha. Okay. There's the sun setting north of west by about 30 degrees. Now, if we look at the equinox, let's see. Let's go to the equinox. If I go to the equinox, clicking date and time, the equinox happens on about March 22nd or so. And we're going to look in the morning. Let's go 8 or 7 o'clock here. There we go. Okay, so again, we're looking south, and if I go back and look at that. The sun is rising due east on the equinox. And that's why we call it the equinox, right? Because the days and the days and nights are of equal length, equinox. Okay, here we go. And we're going to watch this thing rise. And you remember when we were looking at this before, the sun was right here in the wintertime. It was way up here in the summertime, and in the equinox, it's about in the middle. And I think you can figure out what's going to happen here. If we go down, it's going to set due west. Boom. Right there. And that is all due to the tilt of the Earth. Now you can verify this by looking at some other locations. We can't physically go there right now, but we can go there virtually. So let's go down to Antarctica. And just to make it look more like Antarctica, I can go under my sky viewing and change the landscape to something winter. There we go. Okay. They don't have trees in Antarctica, but still looks a little bit better. So here we are. I think we are in Antarctica. Yep, we're in Antarctica. The date and time is let's go back to our summer solstice. Oh, that's nighttime. Right, because in Antarctica, the summer solstice happens in December because the seasons are opposite. So here we are at the summer solstice in the southern hemisphere, and watch what happens if I drive this thing around. What do you think is going to happen? Notice our east is backwards. What's going on here? Right. Oh, I got to do it this way. Okay. Sorry, this changes because we're in the southern hemisphere. I got to use my different coordinate system. Okay, so here we are in the south. We're going to wait for the sun to set here on the summer solstice in the southern pole. Oh my gosh, what is happening? Whoa, north. The sun is just zooming around the sky. Ah, holy cow. Yeah, that's because the sun's not going to set, right? The sun's not going to set because at the pole, on the equinox, or on the solstice, the sun is up all the time. So if we go to the equinox, which is going to be, let's do the March equinox, and I do that again, this is kind of fun to watch. You can chase the sun around the horizon. It just cruises around the horizon and never rises or sets, right? Because it is directly on what's known as the ecliptic, and that on the equinox intersects the equator, and since the equator at the poles is effectively your horizon, you can see that the sun never rises or sets. And then the last one, oh, we can make that go really fast, can't we? Yeah, there we go. Whoop, whoop. Okay. And the last thing we can do is if we go and visit the winter solstice, we should see it's completely dark, and if I run this thing forward, you can see the sky going around and the sun never rises. And the sun never rises because you have 24 hours of darkness, because we are behind. This pole is effectively always in the shadow of the Earth. Okay, let's go back to our PowerPoint. And here's a little picture just to illustrate that. So we were just at the pole, so we're looking down here on the North Pole, right? Here's the equinox. We were at the South Pole, but the same thing for the North Pole. Here's the North Pole and the equinox. You're right at the terminator of light and dark for the entire day, right? So you never see the sun rise or set. It just floats along the horizon. As you go into summertime, you move out so that you, for one day, are entirely in the sun, right? 24 hours of daylight. And then as you move back to the equinox, you're back on the terminator, and then you move back over here, and you're at pure darkness for 24 hours a day for this part of the year during the winter solstice. Okay. So just to remind you of some vocabulary for this, equinoxes are when the Earth's axis are perpendicular to the ecliptic, and we say that the nights and day are equal. That's spring and fall. The solstice is when the Earth's axis is tilted at the maximum angle, 23.5 degrees, and so that's either towards or away from the sun, and then you get winter or summer. And then I put a little vocab summary for you to check out in your book to remind yourself of what these words mean, because there's lots of new vocabulary that we're learning for this.